Imagine for a second that you've got an AI, right? And it's spending, I don't know, 8 unbroken hours just writing Python code. It launches this massive, complex machine learning experiment, and then it just watches the entire system crash.
Which, happens all the time in research.
Right, exactly. But then, instead of just halting or spitting out some generic error message, this AI autonomously pulls up its own execution logs. It parses the stack trace, realizes it, like misconfigured the learning rate schedule, writes a patch, and relaunches the training loop. And it does all of this without a human ever touching a keyboard.
It's wild. I mean, it fundamentally changes the paradigm. We are no longer talking about AI as this highly sophisticated autocomplete tool. We are looking at AI operating as an actual autonomous iterative researcher.
And that is exactly where we're heading in our deep dive today. We are looking at this incredible breakthrough system developed by researchers at UC Santa Barbara and Mila. It's called RTS, which stands for Agentic Reasoning for Tree Search. And the core mission of this deep dive is to look at how RTS is completely overhauling automated discovery.
Yeah, because it's not just trying to outcompute the problem, right? It isn't just running a million combinations faster than a human. It's actually reasoning about its own failures.
Which is such a huge distinction. So to really appreciate the leap forward that RTS represents, I think we have to look at the massive bottleneck in current automated research frameworks.
Right, the old way of doing things.
Yeah. Prior to this, systems that were utilizing, linear search, evolutionary algorithms, or Monte Carlo tree search, like the ARA system, for example, they all operated on what we call score-based heuristics.
Which sounds fancy, but it basically just means chasing a high score. They propose a hypothesis, write the code, execute the run, and then they wait for the validation score.
Just staring at the scoreboard.
Exactly, and if that score drops even a tiny fraction compared to a previous run, the AI interprets the underlying hypothesis as a complete failure. It just abandons that branch of the search tree and pivots to something entirely different.
Which, let's be honest, that seems intuitive on the surface. Like, if you're doing machine learning, objective metrics are your ultimate source of truth. If you introduce a new loss function and the validation error spikes, standard logic kind of dictates you should probably prune that idea and try a different architecture. Why waste expensive compute on a dead end?
Well, that assumption is the fatal flaw here. Score-based heuristics conflate two very different things. They confuse the intrinsic quality of a hypothesis with the quality of its implementation.
Wait, unpack that a little bit.
So you can propose a mathematically brilliant, highly novel neural network architecture, right? A genuinely great idea. But if your implementation contains one minor bug, say a tensor shape mismatch, or a missing normalization layer, or maybe just an overly aggressive data augmentation pipeline, the empirical score returned by the execution is going to be terrible.
Oh, I see. It's like, okay, think of it like judging a brilliant Michelin star recipe as a total failure just because you accidentally set the oven temperature like 100 degrees too high on the first try.
Yes, that is the perfect analogy.
Instead of recognizing the core idea is sound and simply adjusting the temperature for the next attempt, the AI essentially throws the entire cookbook in the trash and decides to make a salad instead.
Exactly. And conversely, think about a thoroughly mediocre, uninspired hypothesis. If it happens to be perfectly coded, it's going to return an average but very stable score.
And the AI likes stable.
Right. The heuristic AI sees that stable score and begins relentlessly optimizing the mediocre idea. It wastes hours of compute exploring this local minimum, while the genuinely groundbreaking idea was just discarded at step one.
Wow. So the real challenge for our task is decoupling those two things. It has to somehow separate the core hypothesis from the physical code execution to figure out why a run actually failed.
And it achieves this by basically structurally separating the brain from the hands.
The brain for the hands. I love that.
Yeah. The workload in RTS is divided between two distinct agentic roles. The first is the scientist agent, which is powered by a high reasoning model, in this specific case, an O3 model. And then you have the executor agent, which is powered by Gemini 1.5 Flash.
So the executor operates strictly as the hands.
Strictly the hands. It writes the Python scripts, runs the bash commands, and manages the entire compute environment.
Leaving the scientist completely isolated to focus purely on the research trajectory.
Exactly. The scientist never writes a single line of code. But, and here's the magic, when the executor returns a poor evaluation score, the scientist intervenes using this specialized tool called inspect.
Okay, so what does inspec actually do?
Well, instead of just looking at the final numerical score and giving up, the scientist uses inspect to ingest the raw execution logs, the stack traces, and the really granular training and validation curves. It is essentially forced to perform failure attribution.
Meaning it has to decide whose fault it is.
Right. It categorizes the regression into one of two buckets. It's either idea wrong or implementation wrong.
I am so curious how that actually plays out on a highly complex data set. Like I'm picturing the HMS brain activity task from the paper.
Oh, that's a great example.
Yeah, predicting seizures from EEG spectrograms is notoriously noisy. It's really high-stakes data. How does an AI differentiate between a fundamentally bad model and a good model that just had, a rough training run?
The comparison between the baseline AIR system and ArtSys on that HMS task makes the mechanics so clear. So AirArray starts with a solid hypothesis. It implements a convolutional neural network, a CNN, and it achieves an initial score of 0.513.
Which is a decent starting point.
It is. So it attempts to improve the model by introducing heavy data augmentation. But the score regresses slightly. Now, because AirArray is a score-based heuristic, what do you think it does?
You can immediately assume CNNs are the wrong approach for the data.
Exactly. It abandons deep learning entirely. It pivots to handcrafted mathematical feature extraction, and it catastrophically diverges to a score of 9.43.
Yikes. So it just completely loses the thread.
It threw away the cookbook because of one bad validation check.
Unbelievable.
But now look at ArtSys on the exact same data set. ArtSys proposes a similar CNN, applies the same augmentations, and sees the exact same regression in the score. But the scientist deploys the inspect tool.
Right, it reads the logs.
Yes. By reading the actual epoch-by-epoch logs, the scientist notices that the validation loss curve was still exhibiting a downward trajectory at the very end of the run.
Meaning the model hadn't converged yet. It was still actively learning the features, but the execution simply timed out.
Precisely. The scientist deduces that the heavy data augmentation slowed down the convergence rate, so it categorizes the failure as implementation wrong. The hypothesis, the CNN architecture, is totally sound. The implementation, the number of training epochs given the augmentation, was flawed.
So it sticks with the CNN.
It refuses to abandon it. It adjusts the learning rate schedule, extends the training loop, and ultimately dominates the task. It achieves a score of 0.467, which actually surpasses the human expert baseline.
Wow. That's a profound shift in how we do this. But, recognizing an undertrained model by looking at a sloping validation curve, that makes sense. What happens when a run catastrophically fails right out of the gate? Like when there is no downward trajectory to analyze and the score isn't just suboptimal, but it flatlines completely.
The APTOS diabetic retinopathy dataset provides a brilliant test case for that exact scenario.
Oh, right, the diabetic retinopathy one.
Yeah. During the search, an agent proposes utilizing a connex-based architecture. The executor runs the implementation, and the evaluation metric returns a literal 0.000.
A flat zero. I mean, in a normal automated pipeline, that architecture is getting permanently blacklisted.
No, absolutely. Every score-based AI abandoned the connex model immediately. But the RE test scientist analyzes the logs and notices a severe anomaly in the gradient updates. The learning rate had been set to 10 to the negative 3.
Wait, for a model with pre-trained ImageNet weights?
Exactly.
That learning rate is incredibly aggressive.
Too aggressive.
It caused catastrophic forgetting, didn't it? The gradient updates were so massive they basically wiped out all the pre-trained feature detectors on the very first pass. It gave the model feature amnesia.
The scientist identifies that exact mechanism. It flags the run as implementation wrong, instructs the executor to dramatically scale down the learning rate to preserve those pre-trained weights, and reruns the exact same architecture. And on the very next iteration, the score jumps from a 0.0000 to a massive 0.92.
That's incredible. But, okay, I see a massive trap here, though. Yeah, if you have a system explicitly designed to basically ignore bad scores and stick to its guns, aren't you practically hard-coding the sunk cost fallacy into the AI? Like, if Artis is constantly overriding bad scores by assuming the implementation is at fault, how does it avoid getting trapped in a loop, endlessly tweaking the hyperparameters of a hypothesis that genuinely is just a terrible idea?
It's a great point, and the researchers knew this. So they engineered a highly rigid protocol at the very beginning of the search tree to prevent that kind of architectural tunnel vision. Before the search even begins, the scientist is forced to conduct 3 sequential audits.
Audits, like an IRS audit.
Kind of. During the audit phase, the executor is strictly prohibited from writing or executing any code whatsoever.
So they artificially constrain the agent. What is scientists doing if it can't run experiments?
It is forced to read the raw data files, analyze the schema, and critically evaluate the baseline code provided for the task. The whole goal is to identify structural bottlenecks or inherent biases in the data representation before it commits to a research direction.
Oh man, the Vesuvius challenge from the paper is a perfect showcase for why that audit is necessary.
Yes, the scroll scans.
Right? For those listening, we're talking about detecting hidden carbon ink inside 3D X-ray scans of charred ancient scrolls. It's a famously tough problem. The baseline code for that challenge takes a highly standard approach to volumetric data. It just takes the 3D voxel slices and averages them together along the z-axis to create a flat 2D image, because 2D is vastly cheaper to compute.
And standard heuristic agents will just take that 2D image and spend 8 hours trying to optimize 2D convolutional networks to find the ink.
But the ink on those scrolls is radiolucent, and it's only microns thick. If you average the 3D slices together, you are physically flattening and destroying the subtle morphological structures of the papyrus. I mean, it's like trying to read a book by blending it into a smoothie first and then analyzing the pulp.
Yeah, that is not going to work. And the RTS scientist spots that exact flaw during the audit phase. By just reading the baseline script and the data descriptions, it realizes that compressing the z-axis destroys the signal.
Before it writes a single line of code.
Exactly. It notes in its audit log that no downstream architectural tweak can possibly recover data that was destroyed in preprocessing. So, from step 1, ArtTest completely bypasses the entire branch of 2D models and focuses exclusively on 3D architectures. It completely dodges a massive dead end that traps literally all the other agents.
Okay, so the audit prevents initial tunnel vision. But as we move, hours into a complex search tree, how does ArtTest ensure ongoing diversity? Because if I ask an autoregressive language model for the next logical step in a research pipeline, the decoding process is naturally greedy, right? It's going to output the most statistically probable, highly conventional next step. It tends to converge on the safest, most boring ideas.
To counteract that greedy decoding, ArtTest employs what they call verbalized sampling. The scientist is never allowed to just propose a single next step. It must generate 5 distinct, mutually exclusive hypotheses across different research axes.
So it's basically forced to brainstorm.
Right. For instance, hypothesis 1 might alter the loss function. Hypothesis 2 might introduce a novel attention mechanism, and maybe hypothesis 3 changes the data normalization strategy.
Forcing the model to explicitly map out a diverse possibility space.
Furthermore, the scientist must assign a subjective probability score to each of those 5 hypotheses, indicating its confidence in their potential. But, and this is the crucial mechanism, the scientist does not get to choose the path. An external sampler function takes those probabilities and selects the next node to explore.
So by decoupling the generation of the ideas from the selection of the ideas, you prevent diversity collapse.
Exactly.
Even if the scientist is 90% confident in a very standard approach, the external sampler will occasionally force it down the 10% path. It basically injects artificial serendipity into the research process and forces it to explore edge cases.
Which is brilliant. That structural diversity is what makes the reasoning engine so powerful. However, it introduces an entirely new, catastrophic problem.
Of course it does.
We are talking about an autonomous agent running for 8 hours, generating dozens of complex hypotheses, reading hundreds of lines of execution logs, and writing massive Python scripts. This creates a severe context crisis.
Oh, sure. The longer the agent runs, the more context it consumes. Even with modern massive context windows, you start dealing with severe attention degradation. The model's ability to recall a specific gradient failure from, say, 6 hours ago starts to slip. It loses the thread of its own research narrative and starts proposing hypotheses it has already proven false.
Exactly. The O3 model, despite its massive reasoning capabilities, begins to literally drown in its own search history. So, to solve this, the researchers introduced an evolution of the system called ArtS*. And their solution is highly counterintuitive.
What do they do?
To handle the massive complexity of an 8-hour research run, they completely remove the giant O3 frontier model. They swap the brain out for Quin34B, which is a tiny 4 billion parameter open weights model.
Wait, dropping from a massive frontier model down to a 4 billion parameter model? That seems like a massive downgrade in reasoning capability. How does a model that small handle the context crisis better than O3?
By not relying on the context window at all. ArtStar utilizes test time training, or TTT. Instead of trying to cram the entire 8-hour history of logs, errors, and insights into the model's short-term memory prompt, they continuously fine-tune the actual weights of the 4B model in real time as it explores the search tree.
Wow, so they are running reinforcement learning on the fly. As the model explores the environment, it is actively rewriting its own neural pathways based on the outcomes of the experiments. It's moving the research history from short-term memory into long-term muscle memory.
That's beautifully put. It's an incredibly elegant architecture. To do this without blowing up the compute costs, they use LoRa, which stands for low-rank adaptation.
Right.
Instead of updating all 4 billion parameters, which would be prohibitively slow and honestly cause the model to forget basic Python syntax, LoRa freezes the base model and only updates a small low-rank matrix of weights.
It allows the model to learn the specific meta-skill of navigating this particular research problem without destroying its foundational knowledge. But wait, how does it calculate the reward for that reinforcement learning? If the whole point of ArcGIS is that intermediate validation scores can be misleading, you can't just use the validation score to update the weights, right?
No, you can't. That's why they utilize GRPO, Group Relative Policy Optimization. GRPO is fascinating because it doesn't require a separate, massive critic model to calculate a baseline reward. Instead, it just evaluates a group of the model's outputs relative to each other.
Oh, that's clever.
Yeah, it aligns the intermediate reasoning steps, like the quality of the failure attribution, the diversity of the verbalized hypotheses, with the ultimate success of the tree search. The tiny 4B model essentially learns how to be a better scientist on this specific dataset, minute by minute.
And the MetaMaze task demonstrates exactly why baking that knowledge into the weights is superior to relying on a massive context window.
It really is the crowning achievement here.
Yeah, so for the listener, MetaMaze is this highly complex, partially observable environment. The agent has to navigate a maze, but it doesn't have a top-down view.
Because it can only see its immediate surroundings, it is mathematically impossible to solve the maze using a standard feed-forward network. The agent absolutely must construct a model with a recurrent memory architecture, like an LSTM, to retain a stateful history of where it has already explored.
Right. And the heuristic AI, AIRA, identifies that an LSTM is a standard approach for reinforcement learning memory. So it proposes the architecture. But LSTMs are notoriously unstable to train. The initial implementation suffers from vanishing gradients, the score crashes, and AIRA abandons recurrent networks entirely. It never solves the maze.
Classic heuristic failure. Then the massive O3 model attempts the task. The scientist reads the audit data, recognizes the partial observability of the environment, and explicitly verbalizes the need for an LSTM. It generates the hypothesis.
Yeah, so O3 gets it.
It gets it. But because the context window is becoming bloated with failed runs and stack traces, the generative decoding process just gets lazy. The sampler continually routes the agent towards simpler, stateless architectures because they are easier to code and debug. It knows it needs an LSTM, but it fundamentally procrastinates because the context burden is just too high.
It's cognitive overload.
Yeah.
But when you look at ArtStar, the tiny test-time trained 4B model behaves entirely differently. Because the lessons of the search tree are actively altering its weights via GRPO, it isn't burdened by a massive, messy prompt.
Yeah.
The imperative to build a recurrent architecture becomes an intrinsic bias in the weights themselves.
Yes. The Qwen3-4B model commits to the recurrent direction. It writes the LSTM, encounters the exact same instability issues, but instead of abandoning it or getting distracted, it iteratively debugs the gradient flow, stabilizes the training loop, and completely masters the environment. ArtStar achieved a score of 53.0 on MetaMaze,
outperforming the absolute best human baseline of 52.50. A 4 billion parameter model defeated not only the human benchmark, but the state-of-the-art frontier models, simply by structurally absorbing its own trial and error process into its parameters.
And the economic implications of that architecture are staggering, because ArtStar relies on a heavily optimized 4 billion parameter model rather than a massive, API-gated frontier model. It achieves superior reasoning and automated discovery at a 5 times lower inference cost.
Getting better performance while radically slashing compute costs is the exact bottleneck the entire AI industry is trying to solve right now.
And the results really speak for themselves across the board. The researchers benchmarked the ArtS framework across 22 distinct, highly complex machine learning tasks, ranging from medical imaging to natural language processing to reinforcement learning environments. ART has outperformed all existing automated methods in 16 of those 22 tasks, driving a 15.3% improvement in the mean normalized score.
What we're looking at is really a fundamental maturation in how AI systems solve complex problems. I mean, the instinct to endlessly optimize for an immediate high score is just a fragile approach to research. True scientific discovery requires the structural patience to look at a catastrophic failure, parse the underlying mechanics, and systematically separate a bad idea from a bad execution.
It shifts the focus entirely from rapid iteration to actual agentic reasoning. When an AI can accurately attribute failure to the implementation rather than the hypothesis, it unlocks branches of the search tree that standard heuristic models prematurely abandon.
Which brings me to what I want to leave you, the listener, with today. Just a final thought to mull over. We just explored how a tiny 4 billion parameter model, a model you could literally run locally on a high-end laptop, managed to beat massive trillion parameter frontier models at highly complex scientific discovery. And it didn't do it by possessing more raw knowledge, but by possessing the architecture to iteratively learn from its own mistakes in real time. So as we look at the massive capital being poured into building larger and larger server farms to train ever larger base models, you have to ask yourself, are we approaching an inflection point where the sheer scale of an AI's parameters matters far less than the quality of the mistakes it is structurally permitted to learn from?
The capacity to adapt through targeted failure is proving to be a far more potent metric of intelligence than raw compute power.
We really might be exiting the era of the AI that just gives you an answer and entering the era of the AI that rolls up its sleeves, burns the souffle, figures out why the oven was too hot, and rewrites the recipe. Thanks for joining us on this deep dive.